All right, now that you survived 1-6 day one, the mega video for all the parent graphs, today we just need to figure out and deal with one last kind called piecewise defined. So our essential question for today is how can I identify and graph piecewise defined functions? So piecewise did talk about a little bit in algebra 2, but we'll be doing a lot of that because a lot of times when you're looking at real life, again, our goal, trying to describe how something behaves, it changes over time. Things aren't always doing the same thing. So if you're looking at sales, might grow for a while and then it goes down or it's constant. So it's constantly changing. So it's not necessarily going to be defined the same way for all parts of its domain. So piecewise is a way to identify that. But before we get started with piecewise, we're going to do a quick review. I'm going to have you pause the video once I give you the directions here. I want you to go through without peeking back, see if you can sketch an example of each of these and understand what each of them look like by their names. So constant function identity, absolute value square root, quadratic, cubic, reciprocal, or rational was the other name for that, and then greatest integer. So go ahead, pause the video, see if you can come up with what each of those look like. Think about what their domains are, their ranges, what are they increasing, decreasing, do they have any symmetries, and then also do they have any intercepts or zeros? Think about those key pieces of information about each one, and then go ahead and come back and check your answer. Alrighty, so let's see how we did. So constant function, value is always the same. So y equals a number. So domain is all reals, range only whatever that output is. Identity function, y equals x, or f of x equals x. Remember, we can write them in their function notation form or just their y equals. Identity, 1, 1, 2, 2, 3, 3. The x value is the same as the y. Domain all reals, range is all reals. All right, absolute value, the v shape, f of x equals absolute value of x. Domain is all reals, but the range, only 0 and above. So it starts at 0. It has y-axis symmetry. So y-axis symmetry. Square root function. Remember, you can't take the square root of a negative number. So the domain is only the value 0 and above. Has no symmetry. It's increasing for all values of x. That's the square root function. Let's talk quadratic and cubic. So x squared and x cubed. Different symmetries. Quadratic functions have y-axis symmetry, remember? And cubic functions have what we call origin symmetry. A point on one side equidistant from a point on the other side of the origin. Quadratics, decreasing first, so from negative infinity to 0, and then increasing from 0 to infinity. Domain is all reals. Range, though, again, only the numbers greater than 0 for quadratics. Cubics, domain is all reals, range is all reals. We don't have any limitations there. And they're increasing for all values of x. Rational or reciprocal function, 1 over x. This is where we had those vertical asymptote as a key feature at x equals 0, and then a horizontal asymptote at y equals 0. So two key features of the reciprocal function. Origin symmetric, so symmetric with respect to the origin, but we have that undefined place at 0. And then our last one that we did on day one was greatest integer, or the other name for that, remember what it was called? Looks like a set of stairs, so they call it the step function. So it looks like little steps. So remember, everything rounds down. So when you take those values, so like f of 2.1, that would be your round down to 2. And remember what the notation looks like for that? F of x equals, it's a double bracket here. There we go. So double bracket, that's the greatest integer function. All right, so let's talk about our last new type here for day two. So we're going to talk about a piecewise function, what that means, and how we can use that to describe real world situations. All right, so a piecewise function is defined to be two or more equations over a specific interval of the domain. So instead of just having one equation like it's y equals 3x and it's for all values of x, what we might have is there's a linear equation from negative infinity to 0, but then we have a quadratic equation from 0 to infinity. So there's two different rules that are being put together to make this entire picture. So you're graphing specific rules on their part of the domain. So as the domain moves through, you have a different rule to represent each of those pieces. So really to graph it then, you graph each equation or rule separately for its specified domain. So for this particular part of the domain, I'm going to use the rule that goes with it. So you can have tons of different ones of these. So the more rules you have, you're just going to have more intervals of the domain, and you put them all together to make the complete picture. So that's what a piecewise function is. And we've alluded to that. We've talked about it and looked at those before earlier in the chapter when we talked about just being able to read a graph. Now we're actually going to do the graphing for one of them. So we're going to do an example so we can talk about what piecewise, how we deal with it and how we work with it. So when you see a piecewise function, what you're going to see is this brace. So you're going to see a brace up front. So this is an additional example that we need to practice what this looks like. When you see that brace, it means, hey, all of these pieces are coming together to make this entire function. So let's take a look at what our two pieces are. So here's the first piece. And when you see the comma, I'm underlining this. This is piece number one. Now you don't have to number it, but for me, that makes it a little bit easier to talk about. So our first equation is f of x equals negative 1/2 x minus 6. Okay, so let's think about what kind of graph this is. That's a degree 1, so it's linear. If it's easier for you and you don't like the function lingo, remember that's the same as y equals negative 1/2 x minus 6 as well. So this is the first equation. Now, when are we supposed to graph it? Well, they don't want the whole line. I know everybody knows how to graph that. If you were just on all real numbers, what you do, I'd probably go down to -6, right? And I'd put the point there, and then I'd do my slope down 1/2, down 1/2, and drawing that whole line. Now, here's the thing, though. I'm not supposed to draw on the whole line. I only want the line for this part of the domain. This is only for the x's that are less than or equal to -4. So starting like back here, I only want that part of the line, not this piece over here. So I only want it over this part of the domain. So in order to be able to make this sketch, just kind of visually think about it, I like to write out those equations and actually find points and values on that particular part of the domain so I can plot those. But again, remember, we're thinking about like this, there's this entire line here, but the only part that I want is the part for the x's that are less than or equal to -4. So this is kind of your cutoff point. I'd only be looking for that part of that line. All right, so how do I get those specific points on there? The easiest way for me is to go ahead and just make a quick little table of values. Always put in the place where this domain interval is changing. So whether it's going to be an open or closed circle, though, is the value included or not included depends on what? Can you guess? What would you look at to determine if -4 is part of the domain that you're using or not? Take a quick peek at that. Less than or equal to, that means it's included. So if it's included, to show that graphically, how do we do that? Well, we're going to use a closed circle, a closed dot to show that, yep, that point's included. So when I plug in -4, that's going to be a closed dot on the graph. So if you plug in a -4 into your equation, you're just going to do that arithmetic and solve. So when you plug in a -4, your value and your output would also be, looks like -4, right? Because that'd be 2 minus 6, so also -4. So we're going to have a point at -4, -4, and it's going to be closed. Okay, now how can I find it? We know it's linear. I need at least one other point. Well, you could do another value. You could just plug in another one. We want an x that's less than -4, so be careful. I could do something smaller than -4. So I could do -5. But is that easily divisible by the 1/2? Well, not really, or multiply by the -1/2. So I'm going to do -6 instead, because then when I plug in -6, it might be a little bit easier to be able to simplify and see what that is. So that would be a -3. All right, so we're at -6, -3, which would be about there. Another way to do it, instead of plugging in a point, don't you have a slope already? So what if I go up 1, back 2? Great. That works super well. Now, when you do this, it's all the numbers less than. So it's going to be there. And actually, since I did this equation written in green, I'm going to go ahead and do this part in green so we can color code. So I can keep going up 1/2, get another point on that ray, that specific part of the domain. So remember, the rest of the line would continue over here. I don't want that, though. That's not the piece I'm looking for. I only want the piece that's less than. All right, so part number 2. So I had 2 rows in this rule. So the second rule is x plus 5. So I'm going to do rule number 2 over here. F of x equals x plus 5. Sometimes it's nice to write it out. Or y equals x plus 5. So that's another linear equation, like an entire line. But I don't want the entire line. I only want it for the x's that are greater than -4. Okay, so notice no equal to. So it is not included. So that -4 is not included in this part. That means when I graph it, it's going to be an open dot. So now let's be super clear on this. So I have to go all the way up to -4. So when I make my table of values, I'm still going to put in that value, that one where the interval ends, it's just going to be an open circle on my graph. So when I plug in -4 into this rule, so -4 plus 5, that's going to give me 1. So at -4, 1, it's going to be an open circle. So I'm still holding the value for that. It's just not included. Now, again, I need another value, so I need something bigger than -4. So how about -3? So -3 plus 5 would be 2. So at -3, we're up at 2. Now remember, the slope is also a way we could find another point. The slope is 1, so up 1 over 1. For lines, that's really easy to do. For things that aren't linear, you might have to do some more values in a table. All right, so since it's linear, it's going to continue that way. Now remember, we should have a y-intercept of 5, so your graph should be crossing the y-axis at 5 as well. Notice that's the only part, that only piece of that graph that you're going to have. And again, the line would continue down into quadrant 3, but I don't want that piece of it because this is only for the x's that are greater than -4. So together, these two lines, or line segments, I should say, rays, come together to make this piecewise graph. Now notice the two pieces don't connect to each other. Sometimes when you finish one piece, the next piece starts right there. This one would be called discontinuous. So when you put dis in front of something, it means not, so not continuous. In other words, you can't draw this entire thing without lifting your pen or pencil when you put it together. So it's a discontinuous graph, and actually this kind of discontinuity where we have this jump between is called a jump discontinuity. So you'll hear that word later on. But piecewise graphs can connect, but they don't have to. The more pieces you have, the more intervals of the domain you have to take a look at. All right, so we're going to do one more example just to practice piecewise to make sure we're okay. And I think we should be in pretty good shape. So here's what I'd like you to do first. Take a look at this one and write out what your rules would be. So what would be the rules that you would need to be graphing and for what part of the domain? So go ahead and pause the video and do that. Alrighty, so I'm going to write these out. I'm going to color code again too, because I think for just visually it's easier to see. And sometimes people will do that even on their own graph. So if you have colored pencils, if that's easier, let's take a look. So each row means a different rule. So there's 3 rows in the brace. That means there's 3 different rules. So the first rule is y equals 4 minus x squared for all the x's that are less than -2. So when I start setting up my table of values for this one, and we'll go back and do this, that means I'm going to definitely have to do -2 for sure. But I'm going to also probably have to do some values that are less than that to see what that shape is. Now 4 minus x squared, that's degree 2. So we're talking quadratic here, a U shape. But we may not see the whole U, right? Because if we're only doing the x's that are less than -2, we're probably going to be chopping this graph off. And we're probably, oh, actually, I should draw it the other way. How do I know I should draw it the other way? 4 minus x squared, that means that leading coefficient is negative. So I'll do one that's going to be more representative of what you're going to see. So you're going to have part of this parabola. You're not going to have the whole thing. So you're probably going to be cutting it off somewhere that maybe you're only going to see part of the branch. You're not going to see that come to a max and then back down to a min. So we have to be careful, how we talked about earlier, that we need to do enough values so we're going to be able to tell what this looks like. So I know I'm going to do -2, but I might want to do -3, -4, just to do a couple other values to make sure I have what I need. So let's go ahead and see if we can calculate those. So if you plug in -2, that should give you, go ahead and pause the video so you can try them. So 0, -3 is -5. And then -4 would be -12. So we're going to graph those and see what that looks like. Oopsie daisy. See if I can move this. Oh, that's pretty. Move that end over. There we go. That's what I'm trying to do. All right, so let's go ahead and graph those points. Now, open or close? Well, if we look at this, it is less than. So that means it's open. It is not included. We need to put in -2. That's an important point, but it's going to be an open circle. So -2, 0 is open. -3, -5. And then we'd have -4, -12, which would be down there. So we have this part of the parabola. Now, I know that this parabola, this 4, means it goes up 4. So if I was going to do the rest of the parabola, it would go up to here and then come back down, right? So I'd have all this whole graph. But I don't want that whole graph because the only part of the domain that this graph or that piece is defined for is for the part from -infinity up to -2. That's what this means. That means negative infinity to -2 is the interval of the domain that I'm using that quadratic equation. So that's that first piece of my graph. Okay, so what's the second equation then? My second equation is, oops, looks like 3 plus x, the red one. So let's see if I can get this one. Yeah. Oop. We got things going both directions here. There we go. So y equals 3 plus x, and that's from -2 to 0. Now notice this one has 3 pieces, so my domain is actually an interval from one number to another number. It's not infinite on one end. Well, these are even better because that means what I need to do is I have to put in the -2 and I have to put in the 0. I need to see what's happening at both ends. Now, if you need more numbers in between to see what the pattern is, great. If you don't, then go ahead and just graph. In this case, that's linear, right? Degree 1. So we know what it's going to do. So I just need to put in -2 in for x. So 3 plus -2 would be 1. And then put in 0. So 3 plus 0 would be 3. So I know what the endpoints are. Now, open or closed, are they included or not? Well, the first one has an equal to. So that means included. Closed. And then the second one is just less than. So that means that one's going to be open. So the first part of the line segment is going to be closed. The second part's going to be open. So let me grab this end here. Oops, and see if I can get that to come over here. All right, so we're going to do, why won't that edge come over? Maybe. All right, well, I guess we're not going to be able to see that. All right, so let's go down here. So it's -2, 1. So close there. And then 0, 3, which is open. And we have that little segment in between. Oops, a little off there. So we have a linear segment for that middle piece. All right, then the last piece is quadratic again. So y equals x squared plus 1, which again, we know what that shape would look like. X squared plus 1, the whole graph would be this. But we're not going to see the whole graph. We're only going to see it for the x's that are greater than 0, which means that piece of it. So we're cutting this graph off and only doing this part. Okay, so let's see if we can get some points on there that would be good to work with. So of course we need to do 0 because that's where this interval starts. And we want the x's that are bigger. So I don't know, 1 and 2. So if we put in 0, we get 1. If we put in 1, we get 2. If we put in 2, we get 5. And is it open or closed? Equal to, included, closed. So we have 0, 1 is closed. And then we have 1, 2, and then 2, 5, and it gets us that nice parabola, right, that we knew, right, this parabola that's shifted up 1, but we're only seeing this half of the graph because we have the x's greater than 0. So 3 pieces. Again, this one's discontinuous, so the pieces don't come together, but sometimes they do. So this is a discontinuous graph, and it has jump discontinuities. Again, it jumps between values. But if you pass a vertical line across this graph, is it a function? So that's my question. They say they're piecewise functions. So is it a function? If you pass a vertical line, will you only touch one point? Absolutely. The reason this works is look at these places where you're probably wondering or a little bit worried. Look at those places where you have points lined up. So these two. One's open and one's closed. So we're able to see that you're not going to have a situation where you have 2 y values for one x value. There's only one that's included. And that's what a piecewise function is all about. So we have different rules for different parts of the domain. So we just graph each of those separately. And you can do this on your graphing calculator. There is a way that you can put the pieces in with those values, and we'll take a look at that at some point as well. But important that you know how to graph them by hand. You understand what that looks like.